All right, buckle up, everybody, because today we're taking a deep dive into some seriously mind-bending cosmology.
Well, yeah, we're going deep on this one.
We're tackling a research paper with a title that's, well, it's a mouthful. Um, it's called Supersymmetry Inversion and the Generation of Dark Matter and Dark Energy from a Helium Bose-Einstein Condensate Singularity.
Definitely a title that grabs your attention.
Yeah, catchy title, right. But it's not just the title that's got people talking. This paper is proposing something truly radical? A completely new model for the origins of the universe.
It really is a whole new way of thinking about how everything began. We're not just talking about tweaking the edges of the Big Bang Theory here. This is a complete reimagining.
Okay, so, like, scrapping the Big Bang and starting from scratch.
Pretty much. And our mission today is to break this complex paper down into, digestible pieces. So you can walk away feeling like, okay, I get the core arguments, even if I don't understand all the nitty-gritty details.
That sounds good to me. But where do we even begin with something this massive?
Well, let's start with the mystery, right? The big unknowns that this paper is trying to solve. And those are dark matter and dark energy.
Ah, yes. The cosmic enigmas. We know they make up the vast majority of the universe, but we can't see them, can't directly detect them. It's like they're invisible, but have this massive gravitational pull.
Precisely. And the thing is, our current best model for particle physics, what we call the standard model, it does an amazing job explaining a lot of what we observe in the universe, but it kind of falls short when it comes to dark matter and dark energy.
So it's like we have this map of the universe. It shows us all the continents, all the familiar landmarks, but it leaves out these massive invisible islands that we know are out there.
That's a perfect analogy. And that's where this paper's alternative approach comes in. They're suggesting that the key to understanding these mysteries, these invisible islands, lies in something called the helium-BEC singularity.
Helium-BEC singular. Okay, you officially lost me. What in the world is that?
It does sound a bit like science fiction, I'll admit, but bear with me. To get there, we need to understand what a Bose-Einstein condensate is, or BEC for short. Imagine you take a bunch of atoms, right, and you cool them down to almost absolute zero.
Like colder than coal.
Way colder. We're talking about temperatures so low that the atoms start behaving in really weird ways. They basically lose their individual identities and merge into this single unified wave. It's like they become one giant superatom.
Okay, I vaguely remember this from physics class. It's like when those synchronized swimmers all become one giant blob, right?
Yeah, that's the idea. And this unified state of matter is called a Bose-Einstein condensate. Now, this paper proposes that the universe started as a BEC, a giant superatom of helium. And that's what they call the He-BEC singularity.
Hold on. So instead of the universe starting with a hot Big Bang, this paper is saying it all began with a super-cooled giant helium atom. That's pretty wild. And this giant helium atom, is that where all the dark matter and dark energy we observe today came from?
You got it. That's exactly what they're proposing. But there's a catch. There's this pivotal event they call the supersymmetry inversion, which transformed this He-BEC singularity and basically kick-started the formation of everything we see today.
Supersymmetry inversion. All right, now we're getting into the really interesting stuff. So what exactly happens during this SUSY inversion? Is it some kind of cosmic explosion?
It is definitely explosive.
Yeah.
Imagine a sudden burst of alpha particles shooting out from the He-BEC singularity. And get this, they're moving faster than the speed of light.
Wait, faster than the speed of light? I thought nothing could travel faster than light. Isn't that like a fundamental rule of physics?
You're right. According to Einstein's theory of relativity, nothing can travel faster than light within space-time. But remember, this model is proposing something entirely new, and it operates outside of our conventional understanding.
Okay, so they're bending the rules a bit. All right, I'm intrigued. So how do these faster-than-light alpha particles connect to dark energy?
Well, that's the core argument of the paper they're proposing, that these alpha particles bursting outward, they are dark energy. In fact, they say that dark energy initially made up a whopping 75% of the universe.
So dark energy isn't some mysterious force. It's literally particles, alpha particles, that were flung out from this giant helium atom at the beginning of the universe. Mind blown. But what about dark matter? Where does that fit into all of this?
Great question. So while all these alpha particles are shooting outwards, the paper also describes an inward movement happening simultaneously.
So it's like a cosmic tug of war. What's heading inwards toward the singularity?
That's where dark matter comes in. The paper suggests that other fundamental particles from the He-BEC are moving inwards, drawn toward the singularity, forming dark matter. And this inward movement initially accounted for about 25% of the universe.
Okay, so it's like a perfectly choreographed dance. Some particles flying outward to create dark energy, while others converge inward to form dark matter. But hold on a second. If most of the universe is made up of dark matter and dark energy, which we know don't really interact with regular matter, how do we get the stuff that makes up, stars and planets and us?
That's where the paper's next point comes, in the decay of both dark energy and dark matter over time.
Wait, I thought you said they don't decay.
Ah, good catch. Should have been more precise. While most of the dark energy and dark matter persists, the paper proposes that a small fraction of both actually do decay. And this decay is what creates regular matter, the 5% we see and interact with.
So even in this wild new model, everything we know and see is still ultimately derived from dark matter and energy. That's pretty amazing. But how does that decay actually happen? What do they turn into?
The paper gets into some pretty fascinating specifics here. For instance, they link the decay of those alpha particles, remember, the ones making up dark energy, to the formation of a stable helium isotope called 32He. And for dark matter, they suggest it decays into antihydrogen, which is made up of a neutron and a positron.
So let me get this straight. Dark energy decaying into a type of helium and dark matter becoming antihydrogen. That's how the matter we know comes to be. So we're all made of decayed dark matter and energy. Talk about a family tree.
You got it.
Hmm.
It's a mind-boggling concept, I know. But it's how this model ties everything together. What's really cool is that this decay process lines up perfectly with what we currently understand about the proportions of the universe today: 68% dark energy, 27% dark matter, and 5% regular matter.
I have to admit, there's a weird elegance to how this all fits together. But you know me, I can't resist asking. Are there any other surprises this theory throws our way?
Well, there are plenty more twists and turns. For one, the paper proposes a revision to the charges of quarks.
Hold up, a revision of quark charges. Quarks are those tiny particles that make up protons and neutrons, right? What do you mean by revising their charges? Why is that even necessary?
You're right. Quarks are those fundamental building blocks of matter. In the standard model, quarks have these fractional charges, like 13 or 23. But in this model, they propose that quarks actually have whole number charges. It's like changing the fundamental recipe for matter. And they do this to maintain something called charge parity.
Okay, you're going to have to explain that one. What's charge parity?
Think of it like a cosmic balancing act between positive and negative charges. The paper argues that by revising the charges of quarks, they can solve another big puzzle: the mystery of the missing antimatter.
Ah, yes. The missing antimatter problem. We should probably remind folks what that's all about.
Right. Basically, the Big Bang should have created equal amounts of matter and antimatter. But when we look out at the universe, we see almost entirely matter. So where did all the antimatter go?
And this paper has an answer to that.
They're saying the revised quark charges actually help account for this apparent asymmetry. In their model, antimatter isn't missing. It's inherently present within the structure of matter itself.
Whoa. So antimatter isn't hiding out in some distant corner of the universe. It's woven into the very fabric of the matter we see every day. That's a game changer. Okay, is that all? Or are there any other cosmological mysteries this model tackles?
Well, there's one more big one we have to talk about: the cosmological constant problem.
The cosmological constant problem, that sounds pretty intense. Break that one down for me.
It's a real head-scratcher for physicists. Basically, there's this massive discrepancy between the predicted value and the observed value for the energy density of empty space, what we call vacuum energy.
So physicists are saying empty space should have a certain amount of energy, but when they try to measure it, the numbers are way off.
Exactly. And the difference is huge. I mean, we're talking about something like 120 orders of magnitude. It's actually considered one of the worst theoretical predictions in the history of physics.
Ouch. That's got to be embarrassing. So how does the SY inversion model take on this seemingly impossible problem?
Well, they offer a new way to calculate the background energy of the universe. But they do it in a really clever way. They factor in the fact that the universe is constantly expanding, the Hubble expansion.
So they're saying you can't just look at empty space in isolation. You have to consider the fact that it's constantly stretching and changing.
Exactly. It's like trying to measure the speed of a river by just looking at a single point. You wouldn't get an accurate reading, right? Because the water's constantly flowing. You need to factor in the movement, the flow of the river, to get a true measurement.
Okay, I like that analogy. So how do they actually account for the expansion of the universe in their calculations?
Well, they bring in a couple of really elegant concepts: the inverse square law and mirror symmetry.
Okay, I've heard those terms before, but remind me how they fit into this cosmic puzzle.
Sure. The inverse square law is all about how things get weaker with distance. It's something you experience all the time. Think about how a light bulb seems dimmer the further away you are, or the sound of music fades as you walk away from the speakers.
Right, right. Makes sense. But how does that apply to the energy of empty space?
Well, the papers suggest that this same principle applies to energy and matter throughout the universe. As the universe expands, the energy density decreases, just like, light or sound weakens over distance.
I see. So they're taking this familiar idea from everyday life and applying it to the energy of the universe as a whole. Okay, that makes sense. But what about this mirror symmetry thing?
Mirror symmetry is all about balance. Think back to how the CIY inversion event created both this outward-moving dark energy and inward-moving dark matter.
Right, that cosmic dance we were talking about.
That's a manifestation of mirror symmetry, a balance between opposing forces or movements. It's like a perfectly choreographed waltz, where every step in one direction is mirrored by a step in the opposite direction.
I'm starting to get the picture. So they're using this idea of things getting weaker with distance and this cosmic balancing act to account for the expansion of the universe and get a more accurate handle on that pesky cosmological constant. But is that all their model does, or is there more to it?
Oh, there's much more. In fact, it doesn't just address the cosmological constant problem. It also offers a more, how shall I say, a more complete and deterministic explanation for how the universe evolved after the SUSY inversion.
Deterministic. You mean it can actually predict specific events or values?
Yes, exactly. The paper uses its framework to calculate specific values for several cosmological constants. And they do it from first principles, meaning they start with, fundamental physical laws and constants.
Okay, give me some concrete examples. What kind of constants are we talking about?
Well, for instance, they calculate the Hubble constant, which, as you know, describes the rate of the universe's expansion. And, get this, they even go so far as to calculate the permeability of free space, also known as epsilon naught, which is a fundamental constant in electromagnetism.
Wow, so this model isn't just offering a vague description of the universe, it's actually crunching the numbers and making very specific predictions. That's incredibly ambitious. But I'm also wondering, if this theory is so revolutionary, why haven't we heard about it before? What are some of the challenges or criticisms it faces?
That's a great question. And it's important to remember that this is still a very new and speculative theory. It challenges a lot of our current understanding of the universe, so it's naturally going to face scrutiny.
So it's kind of like a bold new startup in the world of cosmology. Full of potential, but still needs to prove itself.
Yeah, that's a good way to put it. It's definitely generating a lot of buzz and discussion. Yeah. But it will likely take time and further research to determine if it really stands up to scientific rigor.
Okay. That makes sense. But even if it doesn't end up being the answer, it's still a fascinating exploration of alternative possibilities, right?
Absolutely. And what I find particularly exciting is that it doesn't just stop at physics. The paper hints at potential implications for other fields, like biology and even consciousness.
Whoa, now that's a rabbit hole I'm definitely interested in exploring. How does this physics theory connect to the realm of life and consciousness?
It all comes back to that atomic singularity we were discussing. Remember how the paper proposes that not just the universe, but every single atom has a singularity at its core?
Right. It's like a mini universe inside every atom.
Exactly. And they suggest that this singularity might hold the key to understanding some of the biggest mysteries in biology, like how life emerged from non-living matter and how consciousness arises from physical processes.
That's a pretty bold claim, but how exactly do they connect those dots?
Well, they point out that hydrogen, the simplest and most abundant element in the universe, plays a crucial role in their model. It's, the main ingredient in that He-BEC singularity that kickstarts the whole process.
And hydrogen is also essential for life as we know it. I mean, it's a key component of water, DNA, and countless other biological molecules.
Exactly. So right from the start, there's this inherent connection between the origins of the universe and the building blocks of life.
That makes sense. But how does this atomic singularity play into this?
Well, they suggest that this singularity within each atom, including the hydrogen atom, might act as a kind of a bridge between the quantum world and the macroscopic world we experience.
A bridge. I mean, connecting the weird, counterintuitive world of quantum mechanics to the world we see and feel every day.
That's the idea. And they suggest that this bridge could be crucial for understanding how biological systems function, how life harnesses these strange rules of the quantum world to create, the complex organized structures we see in living organisms.
So they're saying that this tiny singularity inside every atom could be the missing link between the bizarre world of quantum physics and the familiar world of biology.
Exactly. And while they don't go into a ton of detail about the biological implications, they do drop some pretty tantalizing hints. They suggest that exploring this connection could lead to breakthroughs in our understanding of everything from, like, the origins of life to the nature of consciousness.
Now that's what I call food for thought. This deep dive is really pushing the boundaries of what we thought was possible, connecting cosmology, particle physics, and even biology into this grand unified picture. But before my head explodes from all this mind-blowing information, maybe we should take a pause here and let our listeners digest everything we've covered so far.
Sounds like a good plan. We've covered a lot of ground, and there's still more to explore. When we come back, we'll delve into some of the more philosophical and mind-bending implications of this theory and what it all might mean for our understanding of reality itself.
Welcome back, everybody. We're still in the thick of it with this radical new theory for the universe's origins.
Yeah, we're just getting started.
And I have to say, my brain is already doing somersaults trying to wrap my head around all of this.
I hear you. It's a lot to take in, but there's an aspect of this model that I think you'll find particularly fascinating.
Okay, I'm all ears. What's next on our cosmic adventure?
Remember that cosmological constant problem we were wrestling with earlier? That whole issue where the predicted energy density of empty space just doesn't match up with what we actually observe.
Yeah, that whole vacuum energy thing. It's like physicists are saying empty space should be this, this buzzing high of energy, but when we go to measure it, it's practically silent.
Exactly. It's been one of the biggest unsolved mysteries in physics for decades. And, the discrepancy between the predicted and observed values is just astronomical. But this paper, it offers a fresh perspective on the problem.
Okay, so how do they tackle this?
Well, their key insight is that, traditional calculations kind of treat the universe as static, like a snapshot frozen in time. But in reality, we know that the universe is dynamic, it's constantly expanding.
So they're saying you can't just look at empty space in isolation. You have to account for the fact that it's constantly stretching and changing.
Precisely. Think of it like trying to measure the speed of a river by just looking at a single point, right? You wouldn't get an accurate reading because the water's constantly flowing. You need to factor in that movement, the flow of the river, to get a true measurement.
I like that analogy. So how do they actually account for the expansion of the universe in their calculations?
Well, they do it by weaving in a couple of some really elegant concepts. The inverse square law and mirror symmetry.
Okay, those are familiar terms, but remind me how they fit into this cosmic puzzle.
Sure. The inverse square law is basically all about how the intensity of something decreases with distance. It's a really common phenomenon, something we experience all the time. Like, think about how a light bulb seems dimmer the farther away you are from it.
Or how the sound of music fades as you walk away from the speakers.
Exactly. And the same principle applies to gravity, too. The further apart two objects are, the weaker the gravitational pull between them. Now, this paper suggests that this same principle applies to energy and matter throughout the universe as well. As the universe expands, the energy density decreases, just like light or sound weakens as you move away from the source.
So they're taking this pretty straightforward concept and applying it to the energy of the universe as a whole. Okay, that makes sense. But what about this mirror symmetry thing?
Well, mirror symmetry, it's all about balance. Sort of harmony between different aspects of the universe. Think back to that SUSY inversion event, how it created both this outward-moving dark energy and inward-moving dark matter.
Right, that cosmic dance we were talking about earlier.
Exactly. That's a beautiful example of mirror symmetry in action. This balance between opposing forces or movements, it's like a perfectly choreographed waltz where every step in one direction is met with an equal and opposite step in the other.
I'm starting to see the picture here. So they're using these ideas, this idea of things getting weaker with distance and this cosmic balancing act, to account for the expansion of the universe and come up with a more accurate handle on that elusive cosmological constant. But is that all their model does? Or is there more?
Oh, there's definitely more. In fact, this model doesn't just address the cosmological constant problem. It also offers a more complete and deterministic explanation for how the universe evolved after that initial CUA inversion event.
Deterministic? You mean it can actually predict, like, specific events or values?
Yeah, that's right. The paper uses its framework to calculate specific values for a whole bunch of different cosmological constants. And it does it all from first principles, meaning it starts with those really fundamental laws and constants of physics.
Okay, well, give me some concrete examples. What kind of constants are we talking about here?
For starters, they calculate the Hubble constant, which, as you know, describes the rate of the universe's expansion. And get this, they even go so far as to calculate the permeability of free space, which is, it's also known as epsilon naught, and it's a really fundamental constant in electromagnetism.
Wow. So they're not just painting this broad, conceptual picture. They're actually getting into the nitty-gritty, crunching the numbers, making these really specific, testable predictions about the universe. That's incredibly ambitious. But I'm also kind of wondering, if this theory is so groundbreaking, why haven't we heard about it before? What are some of the challenges, the criticisms it might face?
That's a great question. And it's important to remember that this is still a very new and, well, somewhat speculative theory, right? It challenges a lot of what we currently think we know about the universe, so naturally it's going to face some pushback, some scrutiny from the scientific community.
So it's kind of like a bold new startup in the world of cosmology, full of potential, but still needs to kind of prove itself, earn its stripes.
Yeah, I like that analogy. It's definitely generating a lot of buzz and excitement, but it'll take time. It'll take more research and, more evidence to determine whether it can really stand the test of time, whether it stands up to that rigorous scientific scrutiny.
Okay, that makes sense. But even if this theory doesn't end up being the answer, it's still an incredibly fascinating exploration of new possibilities, right?
Absolutely. And what I find particularly exciting, what really gets me going, is that it doesn't just stop at physics. The paper hints at some really interesting implications for other fields too, like biology, even consciousness.
Whoa, okay, hold on a second. Now we're getting into some really mind-blowing territory. How does this physics theory, how does it connect to the realms of life and consciousness?
Well, it all circles back to that atomic singularity idea that we've been discussing. How the paper proposes that not just the universe, but every single atom has this singularity at its core.
Right, that whole mini universe inside every atom concept.
Exactly. And they suggest that this singularity, it might hold the key to understanding some of the biggest, most fundamental mysteries in biology. Like how life itself emerged from non-living matter, and even how consciousness arises from those physical processes in the brain.
That's a bold claim. But how do they actually connect the dots?
Well, they start by pointing out that hydrogen, that simplest, most abundant element in the universe, well, it plays a pretty crucial role in their model. It's like the main ingredient in that He-BEC singularity that, kicks off the whole process.
And hydrogen is also, it's crucial for life as we know it. I mean, it's a key component of water, DNA, countless other biological molecules.
Exactly. So right from the get-go, there's this inherent connection, right? This link between the very origins of the universe and the building blocks of life.
I see. Okay, that makes sense. But how does this atomic singularity actually play into all of this?
Well, they kind of propose that this singularity, which exists within each atom, including, of course, the hydrogen atom, it might act as a sort of a bridge between the quantum world, that world of subatomic particles, and the macroscopic world that we see and experience every day.
A bridge? You mean like connecting that weird, counterintuitive world of quantum mechanics to the more familiar classical world of everyday life?
Yeah, precisely. And they suggest that this bridge, this connection, could be absolutely crucial for understanding how biological systems work, how life manages to harness those strange rules of the quantum world to create, these complex organized structures we see in all living organisms.
So they're proposing that this tiny, infinitesimal singularity inside every atom, they're saying that could be the missing link between this bizarre world of quantum physics and the world of biology, the world we live in.
Exactly. It's this incredible idea that links those two seemingly disparate realms. And while they don't go into a ton of detail about the biological implications, they do drop some pretty thought-provoking hints, Like they suggest that exploring this connection further could lead to some major breakthroughs in our understanding of, well, everything really, from the origins of life itself to even the nature of consciousness.
Okay, now that's what I call food for thought. I mean, this is a lot to process. This deep dive has really pushed the boundaries of what I thought was possible, connecting cosmology, particle physics, even biology, all into this grand unified picture. But before my brain melts from all this information overload, maybe we should pause here for a second. Let our listeners kind of digest everything we've covered so far.
Yeah, that sounds like a good plan. I mean, we've covered a lot of ground, and there's still more to explore. When we come back, we'll delve into some of the, some of the more philosophical implications of this theory and what it all might mean for, our understanding of reality itself.
Welcome back to the show, everybody. I hope you've had a chance to, grab a coffee, maybe take a walk, because we are about to launch into the most mind-bending part of this deep dive yet.
We're going full-on philosophy mode now. Buckle up.
Oh, I am buckled. So before we get too deep into the weeds, let's just recap for a second. We were talking about this idea of the atomic singularity and how the paper sort of hints at a connection between that and, well, some of the biggest mysteries in biology, right? Like the origins of life, even consciousness.
Exactly. Remember, the core idea here is that this singularity, this point of immense energy and potential packed inside every single atom, it might be like a bridge between the quantum world and, the macroscopic world, the world we experience every day.
Okay, yeah. And that this bridge could be the key to finally understanding how life emerged from non-living matter, how our brains, create thoughts and feelings and, well, consciousness. That's a pretty big leap, right?
It is a bold idea, but think about it. I mean, we still don't really understand how consciousness arises from physical matter. We know that the brain is involved, but how exactly does a bunch of neurons firing create, subjective experience? This theory suggests that maybe, just maybe, the answer lies in this realm where quantum mechanics and biology intersect, a realm where the rules of classical physics might break down and all sorts of new possibilities emerge.
Okay, I'm starting to see where they're going with this. But, how does it actually explain consciousness? Do they provide any kind of specific mechanisms or models?
Well, they don't lay out a complete model for consciousness, but they do offer some really intriguing possibilities. For example, they point out that a lot of the strange phenomena we see in quantum mechanics, like entanglement and superposition, well, they suggest a level of interconnectedness and non-locality that we're just beginning to grasp.
Okay, hold on a second. Remind me what those are again. Entanglement and superposition. It's been a while since my last physics class.
Sure. So entanglement, it's when two particles become linked together in a way that, it transcends distance. Basically, if you change the state of one particle, the other one changes instantaneously, even if they're, light years apart.
So it's like they're communicating faster than the speed of light.
It is mind-boggling, isn't it? And then there's superposition, which is this idea that a particle can exist in multiple states at the same time until it's measured. It's like, imagine a coin spinning in the air, right? It's both heads and tails at the same time until it lands.
Okay, I remember those concepts now. But how do they relate to consciousness? How does this quantum weirdness play into, our brains and how we experience the world?
Well, the paper suggests that these quantum phenomena might play a role in how our brains process information, form memories, and generate conscious experience. They propose that maybe, just maybe, those atomic singularities within the atoms of our brain, well, maybe they're interacting in ways that we don't yet understand, creating a kind of quantum network that could be the foundation for consciousness.
So you're saying our brains might be like, these super advanced quantum computers.
Yeah.
Using entanglement and superposition to create our thoughts and feelings.
It's a radical idea, but it's not entirely out of the realm of possibility. And, it really highlights how this theory forces us to think outside the box, to consider these entirely new ways of understanding ourselves and, well, the universe we inhabit.
It's definitely challenging a lot of, my assumptions about reality. But if this theory is right and consciousness really does arise from these, these quantum interactions, what does that mean for things like free will? Does it mean that our thoughts and actions are like predetermined?
That's a great question. And, it's one that philosophers have been grappling with for centuries. This theory doesn't give us a definitive answer, but it does open up some fascinating possibilities. For example, if our brains are really operating at this quantum level, then it's possible that random quantum events, those little fluctuations in the fabric of reality, well, they could actually influence our decisions. And that would introduce an element of randomness, of unpredictability.
So instead of our thoughts and actions being like set in stone, there might be this interplay between, deterministic processes and these random quantum events.
Exactly. It's kind of like rolling dice. You have certain probabilities, certain outcomes that are more likely than others, but there's always that element of chance. You never know exactly what you're going to get.
This is getting pretty deep. It's really making me think about, what it means to be human, to have a conscious experience in this vast, mysterious universe. Are there any other kind of philosophical implications we should consider?
Well, one of the things that this theory really challenges is this traditional separation we often make between mind and matter. The idea that the mind is this immaterial thing that's somehow separate from the physical world. If consciousness really does arise from, the interactions of these atomic singularities, then it suggests that consciousness isn't separate from the physical world at all. Instead, it's an emergent property of it.
So instead of thinking of the mind and body as like these two distinct entities, you should really be viewing them as, interconnected aspects of a single unified reality.
Exactly. It's a much more holistic perspective, a more integrated view of reality. It sees consciousness as, as woven into the very fabric of the universe. It's not something that's separate from it or imposed upon it.
Wow, this deep dive has really been a journey. We've gone from the birth of the universe to the very nature of consciousness, all thanks to this incredibly radical theory.
It's been a wild ride, that's for sure. And, I think it really highlights how science, it's not just about collecting data. It's not just about testing hypotheses. It's also about exploring new ideas, challenging assumptions, and just, really pushing the boundaries of our understanding.
Absolutely. This theory, it might not end up being the ultimate answer, but it's definitely given us a whole new way of looking at the universe and, our place in it. It's made me realize how much we still don't know, how much there is left to discover.
I couldn't agree more. Yeah, and who knows, maybe one day we'll have the technology, the tools to actually test some of these, these mind-bending ideas and see just how far down this rabbit hole goes.
Well, I'm definitely looking forward to that day. But for now, I think it's time to let our listeners go out and ponder all the amazing possibilities that this theory presents. Maybe it's inspired you to question your assumptions about reality or to just look at the world with a fresh perspective, or maybe even to do some exploring of your own.
That's what we hope for. And if you're feeling particularly inspired, I definitely encourage you to seek out the full research paper and really dive into the details. You might be surprised at what you find.
And on that note, I want to thank you all for joining us on this incredible deep dive. Until next time, keep exploring, keep questioning, and never stop wondering about the mysteries of the universe.